All right.
So I'm very happy to introduce you our next speaker, Ilias Gerostathopoulos. That's how you pronounce it?
Pretty much, yeah.
Oh, thank you.
Good try.
He's assistant professor of computer science at Vrije University of Amsterdam, colleague of Ivano, and also a new collaborator with me. He obtained a PhD in computer science from the Department of Distributed and Dependable Systems in the Faculty of Mathematics and Physics, Charles University in Prague. He has spent time as a postdoctoral researcher in the Department of Informatics at the Technical University of Munich, where they will do great stuff on these topics. And his research focuses on software engineering, software architecture, and self-adaptive systems.
Thank you very much, Carlos. Thank you for inviting me also. Actually, I like the event. It's a very nice building. I have been looking around. So today, I would like to talk about self-adaptive systems. And this is my plan for the... Do I have 1 hour still or 45 minutes?
1 hour.
1 hour, okay, good. Let's see if we get there. So first, I would like to kind of introduce a little bit some terms, right? Some definitions. What is, maybe what isn't a self-adaptive system, all right? Then I would like to give you an overview of research in self-adaptive systems. That would take the researcher's perspective, right? In all of this thing called adaptive systems, self-adaptive systems. Then I would like to give you some, perhaps, tips or, let's say, ways to engineer self-adaptation. Actually, we will talk about a lot of those before in this research overview. But here I will probably, let's say, recap and just give you some highlights, okay? Some ways to think about how to develop your adaptive system. Finally, I want to give you some glimpse of a survey that we did with industry. So why, what does industry think about our research in self-adaptation? And then just leave you with some open challenges, maybe something that you can see in your own research, right? That is interesting and you may want to work on. All right. So that said, I'm not from robotics. I'm also not. I'm in software engineering, right? Like Ivano. As Carlos said, my background is software architecture. I don't have a slide about myself, but I will explain. It's software architecture, okay, and adaptive systems. I have been working in this area for, let's say, more or less about the end of my PhD since 2014-15. Okay, so I have some experience, and maybe I didn't do the great work that Carlos said I did in my postdoc. That was 4 years, but I certainly understood better the area. So I will try to give you an overview here today. There is a lot of details in many of those slides and many of those things that I will touch upon. Okay, so just ask me. So interrupt and just tell me, and I will try to explain something more. Or I will try to kind of give you the right pointer, all right? Also, this is probably the most out of robotics talk that the summer school has. So even my examples are not really about robotic systems. So please stay with me, and if it's something boring, tell me to just speed up or just slow down if you want, okay? So that's it. So why and what? Preliminaries. So this is an example just of an adaptive system that we typically use. In our papers, in our research, right? So it is a classic example of, how does this work, of a web-based system, right, that has several tiers. So that is basically the web tier. You can also imagine having a database tier here, or rather the application tier and database tier that I didn't depict in the picture. And it basically accepts user requests from web clients, right, that come to the system through a load balancer, okay? So a very classic, let's say, a website, for instance. Now, what you can do in this system is that you can increase or decrease the number of web servers, right, or application servers. This is known as elasticity. Have you heard of it before? Good. So the other thing is that you can actually decide, the system can decide whether to include or not optional content in the answers to the requests. Okay. For example, optional content might be advertisements, right, or recommendations. So the more optional content you include, the slower your requests will be, right? But at the same time, you will generate probably more profit for your organization. So there is a little bit a trade-off there. So what you would like in this system, what are your goals, is to basically minimize the infrastructure cost, right? Makes sense, right? So we don't want to have our servers kind of always like in maximum number, right? So we want to have just the amount of servers that we need, and not more. Then we want to increase the revenue by serving more ads, if possible, okay? But at the same time, we want to keep some latency, average latency, worst case latency, 90th percentile latency. This is getting into the details, but some latency within some bounds, right? These are essentially your requirements. Now, what can go wrong here, right? Or what you're not sure about. You're not sure probably about the number of requests and also the type of requests, because they might fluctuate at runtime. Sometimes we do see that even at an extreme case. Actually, this whole use case, this whole exemplar, was motivated by something called the slash-dot effect. Have you heard of this before? Okay, some of you have. So basically, a very rapid increase in the number of requests on a web application that causes the web application to crash, right? If it's not elastic, okay? So actually, these things, so the number of and the type of requests, we call them uncertainties, right? That are only known during operation. You might have an idea about them while you design your system, and this lets you also pick, for instance, a range of a number of servers, right? But you don't know exactly what will happen. So these are uncertainties. So this is one reason to make your system, or one motivation behind runtime change. You want to change your system at runtime because of those uncertainties, okay? Just to give you another example, it's a toy example, and you're allowed to laugh if you're really working with much more difficult systems. But a couple of years back, we were looking at this, meaning from the software engineering perspective, let's say. This example of having robots, oops, wrong button. So basically, we actually bought a couple of turtle bots as well, and we basically simulated this example where they have to start cleaning the floor, right? And different tiles get dirty. At least in the simulation, it was easy to make them dirty. That was dirtier than this one, for instance. And then the bots will have to go around and somehow synchronize and then clean the area, okay? Similar a little bit to this example in the morning with drones. So they had to basically survey the area, exchange some information, and then take some decisions. And then they also had some other goals. They also had the goal, for example, to not deplete their battery. So they had to come back to the docking station and charge, all right? And then that was something that we used in our research. Again here, right? What are uncertainties? Things that you don't know, yeah? Some things are like that. So, for example, what if there is an error in the localization of the robot, right? Something that you working with robots, some of you at least, will probably have seen that, right? What if there is something that happens in the environment, for example, the floor of the robot? What if there are more robots joining a group, right? And you need to collaborate in groups of 3, not of 4, not of 3, etc., right? Out of power, we said about that. What if there are some humans interfering with your robot? Okay, so all of these are uncertainties that we need to resolve at runtime. Are you with me? Make sense? Yeah, good. So basically, my point is that modern systems, including robotics, of course, are subject to uncertainties. And there are people in my domain, let's say, in adaptive systems, that have even tried to classify these uncertainties, right? So they say, okay, what types of uncertainties exist? What categories of uncertainties exist? In brief, they have classified, basically, the uncertainties exist in environment of the systems. It's a broad term, I know, but typically we refer to something that is not controllable by our software. This is your environment. Think again, I'm having this software view on things, right? So environment for me would be really even the hardware, many times, right? The users, that again, we can debate and you can say, oh, this is part of the overall environment. Yes, it is, but they are also special kind of, they would typically treat them specially, in a special way, the users of the system. Actually, uncertainty can come from internal functioning. For example, if you have a fault, if your localization fails, right, and you have to adapt to a new module, that's not really the environment or the users, it's the system itself, right? And very interesting as well, even though it's something we don't talk very much about, is that the goals of a system may change. So you might have a system that does A. Actually, robotics is, this goes well with robotics, because in robotics you might have a different mission to do, right? And you want to change this mission at runtime. So this is another thing that you can conceptualize it as an uncertainty, even your goal, all right? So, all right, so now we have the uncertainties. I tried to convince you, but we have another thing in modern systems. We have business continuity. This is essential, okay? So we cannot just take down a server, right, or take down the whole application or we don't want to kind of take our robots back in a safe area. We want to do the fix or do the adaptation right there on the spot, right? And these two things basically points us to the need for handling uncertainties at runtime. And this is the whole point behind adaptation. If we wouldn't have this need, it wouldn't be so exciting to talk about the self-adaptive systems, right? So there are uncertainties that manifest themselves at runtime, and also we need to address them, right, somehow at runtime. Good. Now, I talked about business continuity, and this is boring sometimes. You say business, oh, no, it's all about making money. Think about business in a more, I'm challenging you, think about business in a more, broad way. Think about the business of, putting life in another planet. Actually, NASA does that. Actually, the business of NASA is exactly this. So they want to send robots, perhaps you know, maybe more than me, into other planets, right? And then they are talking, this is some slide I stole from them, about different types of, autonomy, right? Autonomic or autonomous system. They say we have resilient system, this is stage 1. Then we have independent system, stage 2. And we have self-directed system, which, this is interesting, the last one. They say system develops science strategic plan, and tactical plans based on high-level objectives. Responds to novelty by adjusting plans with context of objectives. It's possible to reduce the size of science operations team. See, they point to one more thing. If we make systems more autonomic, autonomous, self-adaptive, runtime adaptive, you pick a word, then not only will we deal with, we will give them business continuity, but there is the element of reducing the effort of the humans, which is crucial because of this. Look at this, another motivation behind adaptation. This is something that shows a graph that shows the gap, right, between the complexity of building software, for the automotive sector, and the productivity of teams. How do we bridge this gap? Right? We see this opening, right? This gap is really bigger and bigger. How do we bridge it? We can hire more people. This is failing globally. More people bring more problems. We know this in software engineering, right? Bigger teams that do not always help, right? You can have more teams. Sure, this is what is happening. But up to which level? So if we make our system smarter, right, they will probably take away some of the responsibility of the operators, of the developers, of the testers, of the maintainers, right? So this is the other motivation behind what we are researching here. Okay, so the main idea behind self-adaptation. Who can tell me what is the main idea behind self-adaptation? It's not a tricky question. To adapt, exactly, yeah. To adapt to what? And according to what criteria?
Well, all those
and when?
Showed. So according to the environment, the goals.
Perfect. All the uncertainties, exactly. So to address uncertainties at runtime. Okay. I think it's something that I have here. I have something like that. So jokingly with a friend of mine, we always say, adaptation is about loops, you know? You have a loop, and then your system is adaptive suddenly. So that's all. Well, okay. That's indeed all, if you want to be very, very, very abstract. But essentially, this is the main idea, right? So we want to basically collect data about the state of a system, the environment, and the goal at runtime, resolve the uncertainties, and adapt to satisfy the goals. For example, in the original system, for example, to increase the profit or to keep the latency stable, right? So this is the main idea. Now, we could stop here and say, okay, now you know what is an adaptive system and what is not. But I was not that satisfied. So I actually will give you something more. It's still not a definition, but it's the only thing we have closer to a definition. We have tried as a community a little bit, and I have also tried myself with some colleagues to give a definition and even a test that we can run and say, this is adaptive, this is not adaptive as a system, right? and we basically failed. I have to summarize it very quickly. So it is a very difficult thing to do, to say what is adaptive, what is not, have a very clear line. So that's the best thing we have, some principles that show us that most self-adaptive systems actually follow, okay? And they are complementary, and they are two. One is the external principle, which more or less summarizes the previous slide. It says an adaptive system or self-adaptive system, I don't differentiate, by the way, at least not in this presentation, can handle uncertainty in its environment, itself and its goals autonomously. Now, that's another point, the human interference, right? That's another point. Even if there is human interference, many times we will say the system is self-adaptive, right? So that's not clear-cut. It's not like, oh, if there is no intervention, the system is self-adaptive, and then if there is, it's not. No. It's not that simple. I wish. Okay, so sometimes we just need to have the human in the loop, we call it. Yeah? The internal principle is the other thing. It's like the engineering view. Typically, a self-adaptive system comprises two distinct parts, all right? So the first part is the one that interacts with the environment and has domain concerns. And then the second part that interacts with this first part and deals with these so-called adaptation concerns, which are, to kind of go forward a bit faster, typically there's some conflict there. There's some trade-off between the adaptation concerns. You see in the first slide, I said profit versus latency versus infrastructure cost. If I would pick only one of them, minimize latency, then I would increase the number of servers. I wouldn't care, right? So there's always some kind of trade-off that you need to resolve at runtime. That is where it actually matters to use these techniques. Okay? Now, to put it in some kind of graphical picture, this is the first principle, essentially, considers a software system in its environment. The software system has some inputs. I always mistake this. Some inputs and basically affects the environment. And then you call it a self-adaptive software system when the input includes some uncertainties. Okay? That's a very simplified view. Now, the second principle actually has a little bit nicer representation. So again, we have a software system, the environment, we start from the same point, and then we look at the system itself. We kind of open the system and we check what it's composed of. And typically, a self-adaptive system will have some instrumentation to monitor and adapt, all right? And then it will have another part, which is basically what this internal principle talks about, okay? Which is concerned with the adaptation. So the managing system is concerned with the adaptation concerns and goals, okay? So what's also interesting is that this managing system receives inputs from the system itself and also from the environment, okay? This is the dual role of monitoring there in the adaptive systems. Is it abstract enough, guys? Or shall I make it more? So this is the more abstract thing we can say about self-adaptive systems, right? So this is a conceptual model. Now, it has basically an adaptive system, a managed subpart, a managed system, and the managing system. The managed system, for instance, in the first slide, in this web application, would be the part of the system that sends requests. The managing that serves those requests incoming, right? The managing system would be the part that basically checks whether the latency is met, and if not, increases the number of servers. Okay? Now, yes?
I have a question regarding this figure and the monitor arrow on the left. Because if there is any architectural layering tactic here, that one is breaking that principle of layering the concerns, for example. So I'm curious about that monitoring, why the managing system has direct access through the environment that is not through the managed system.
Yes, that's a good point. I will try to answer in some slide later when I talk about the MAPE, all right? But yeah, is asking Carlos basically, isn't this breaking this architectural abstraction that we're building? Because essentially, Carlos says, you are tricking us, right? You're kind of building some architecture of a complex thing just to analyze it. But in the end, it's all the same, right? All would be in the same bunch of code, and it's true. This is a conceptual model, right? So it doesn't mean that this is your implementation model. It doesn't mean that the managed system is one system. It can be several robots. It doesn't mean that the managing system is one system. It can be You can have several ROS nodes, right, implementing the managing system. You can have distributed systems. All of this are details that come later. And still, the abstraction problem is something that I still have to comment on. Good point. Does it make sense? The introduction is over. Shall we step into the research overview? Good. So here is basically an attempt that was not mine, was one of the good researchers in the community, Danny Waynes, in Belgium, a full professor there. Actually, he wrote a book I have with me there. And even before that, he did a tutorial and he tried to summarize the research in the domain in 7 waves. Okay? And the waves is a pretty nice idea to say that, okay, we have research trends that overlap over the years. Okay? There are some waves that have been consolidated in a way. So we kind of know as a community where we agree on some things, on some research outputs, and there are some others that are open and active, right? So here comes the big picture of the waves. So first came the part of looking at self-adaptation as automating tasks, all right? Then what we looked at as a community, this is really an attempt to summarize 20 years or in one slide, was the architecture principles behind automation of tasks. Then we looked into the runtime model. So how to, do you know what, have you heard of the phrase model at runtime? Some of you? Yes, some software people? Yes. So basically the idea there is that you have your model, your design model, your SysML model, and you keep a live replica of it at runtime, and you keep updating it, right? And it helps you reason about what is happening at runtime. So that was a big kind of part of this research looking into this. Then others, more or less in parallel, more or less 10 years ago or so, they started looking at the question, okay, we kind of know a little bit the mechanisms of doing adaptation, but why would we do adaptation, right? Why? What are the requirements for adaptation? What are the adaptation goals? So they started creating goal models. Milopoulos' work and Lamsverde work, they really focused on the requirements-driven adaptation. And then using those models, right, to do adaptation at runtime. Then several researchers looked into the problem of guarantees. They said, okay, yeah, we can make systems that sometimes will do what is needed, you know, to fix some problem, but they will create more problems. By fixing A, they will create B and C and D. Or if this happens, that we don't have a way to, you know, react. So what is really, how can we really say anything? Or even, how can we certify such a system? So they started thinking about how to provide some guarantees that are statistical in nature, and I will go through this a little bit more. And then finally, control principles, more or less in parallel, more or less again, about 10 years ago, some people from control theory came to the community and said, actually, we have the right tool for you. It's called control theory, and we have been developing for so many years that now it's so mature and it can solve all your problems. Well, it cannot, but again, I will just go into this a little bit later. But it does solve a lot of problems. Finally, we are now probably the most hot wave, for sure the most hot wave, and we are now in this, is this called learn from experience. So machine learning, essentially, right? So we are really trying to machine learn the heck out of adaptive systems. So we want to basically use classifiers. We want to use regressors. We want to do reinforcement learning. We want to do reinforcement learning with special concerns and constraints, right? And all of these are new techniques that we're investigating right now. Okay, so this is the overview. Now, I cannot cover everything, so I will cover basically 3, 4, 5. This 5, pretty briefly. Sounds good? Still with me? Good. Just checking. Good. Let's look into this automating tasks. What happened there? Basically, this wave is, well, about, I have to really figure out how this works, about the idea that, you know, tasks by human operators, for example, starting or stopping a virtual machine, is very tedious, right? And it needs a lot of effort and also error prone. Some people might get, you know, just have a bad day or you know, drink more or sleep less, or they make mistakes. So why don't we start automating such tasks, right? And what people did actually is that they even went there and interviewed administrators of, let's say, cloud infrastructure. They said, okay, what do you do when this happens? It's actually the way it actually happened. I learned later on, and they told them, well, we do AB3 if this happens. If that happens, we do that, that, and that. So they started collecting this information and then tried to think of what is the right language of capturing these rules. Okay, this was about automation, and it all started from a paper that you might have heard. It's called the Vision of Autonomic Computing. Have you looked at this paper? Have you checked this paper before? It's a pretty nice one to check. It's really a visionary paper, right? 2003, some guys from IBM said, okay, they really wrote sentences like that. They really wrote systems that manage themselves according to an administrative goal. New components integrate as effortlessly as a new cell establishes itself in the human body. They were inspired by, of course, also the human body as an organism, right? Pretty interesting. And they said these ideas are not science fiction, but the elements of a grand challenge, which actually it's still ongoing. We still have the grand challenge of how to develop such systems, okay? And they came up with this. Have you heard of MAPE-K? This famous reference model? Good. So that was first probably in this paper. So basically it is tries to explain, again, a bit conceptually, what needs to be done when you implement this famous loop, right? So it also has these two elements clearly depicted, right? So the managed element, so the managed system, and the autonomic manager, which was in the conceptual model the managing system, okay, from before. So it maps nicely to our conceptual model. Now, there's these four phases of MAPE, okay? Monitor, analyze, plan, and execute. The monitor basically is what also Carlos asked, collects data from the managed element and in execution context. The execution context, the way they explained it then, was actually the environment, okay? The analyze phase is once we have collected the data, we try to analyze basically, are our goals met or not? And what are our options in order to meeting those goals? Can we do, for example, some pre-filtering of our options? This all goes into the analysis, right? The plan phase, essentially, will only be executed if there is a need, right? So if we found out that, for instance, yes, we are not making much profit and this is bad, all right, so let's then trigger the planning phase, which will basically create a plan. And that, again, depends on the specific system, and also there are different ways. I will talk a little bit about the different ways of doing these phases, right? Of basically doing different actions, increasing or decreasing the server, or increasing or decreasing the dimmer value, right? The number of advertisements, etc. Finally, the execute is simple because basically it takes the plan, which might be composed of several steps, and tries to kind of execute it down to the system, right? And most interesting part actually is not these phases, it's probably the K. And this is nice because basically the K, the knowledge, is an abstraction of the relevant aspects of the three things. Managed element. If you have an abstraction of the managed element of your system, this is typically what is called self-awareness, right? It connects nice also the word that we hear. If you have an abstraction of the environment, of the context, this is typically what we call context-aware or context awareness, right? And okay, that's something that probably I will term right now. The goal awareness is the awareness of the goals of your system or of your administration in that case. All right. So one might say, okay, perfect. So basically, a self-adaptive system will be also self-aware and context-aware at the same time, right? If we believe this. So of course, the abstraction of the managed system that enables you to be self-aware is basically one element of monitoring. The other, the model of the environment, and that enables context awareness, is the other reason for having the monitoring phase. Okay. So, does this make sense? Yeah. Good. Now, what happened next? So that was kind of, okay, it started off things, and many people said, okay, this is very exciting, let's work on this vision. Then a lot of people started looking at it from the perspective of architecture. They said we need to put structure on the code that we build, okay, on the systems that we build. And basically, we need to bring structure because we want to have a principal way of building such systems. And okay, maybe you heard from the previous talk, but what do you think is the main driver or the main reason for kind of looking at an architecture of a system? Ivano mentioned a couple of reasons. So why to care about an architecture of a solution or for a system? Maintainability, thank you. That's a very good point, of course. Maintainability is one of the main reasons. Also to explain, basically, to be able to communicate, right, decisions in your software. These are all important things, especially if you build like complex loops, right? So you want to be able to maintain them, and not solve a problem and create 14 more. I was actually told in one of the presentations in my early, I think it was during my PhD, one of the professors stood up at the end of my presentation and told me literally, okay, I see why what you present solves one problem but creates 1, 2, 3, 4, 5. And he was actually right, but I couldn't really answer. So indeed, many of the solutions, you know, that we build in this community, it's a fun place to be. You know, you just find the problem, you say, okay, I will do the, you know, I will show how smart I am by devising a perfect solution that solves that problem, but then creates other problems. So we need the proper abstractions, right? So this is something that became quite famous, apart from MapeK, something that Kramer and Maggie more or less got inspired from robotics. And they wrote a paper in 2007, and they wrote something like this. They wrote that the architectural level seems to provide the required level of abstraction and generally to deal with the challenges posed by self-adaptation, right? And this is, do you know of this model? Have you heard of this model before? Of this 3 layers model? Or perhaps of this work, the 3-layer architectures? Some of you? Curious, no? Yeah, good. So basically, this is something that connects actually pretty well to robotics as well, because it was inspired from it. So the 3 layers are goal management, change management, and component control. So basically, the goal management would be responsible for this kind of replanning. The change management for executing the lower layer, and the component control will basically be the actual functionality of the system. So you can try to map this to the conceptual picture. What would be a managed element? What would be a managing element, right? So probably all of these components will be elements of your managed system, and the way you compose them together, that will be something that comes to the managing system layer as information. Okay. So essentially, again, the component control is a set of interconnected components, and then you basically have facilities to do this reflection at the upper layer. And at the upper layer, basically, you are monitoring whether you're still on track with a certain mission or a certain goal in your adaptive system. And if you're not, then you basically delegate and you do some kind of actions to kind of steer the operation to, or steer the system, you know, towards one direction. And if it's out of your hand, because basically, for instance, the administrator said that, okay, our mission is now different, then you again delegate, okay? So the important thing is that the layer on top does not really know or care what happens to the layers in the other layers. That's a basic abstraction functionality that we are after here, because by this we're conquering a little bit the complexity. That's another reason for having an architecture, principal architecture, right? So you structure things in a way that you can then well, maintain, but also continue to develop, right? Good. So, okay, maybe this one you will enjoy more. So, guarantees under uncertainties. So, what happened here is that we had some mature solutions for engineering self-adaptation, but uncertainty was handled in an ad hoc manner, as I said before. sometimes the solution would work, sometimes it wouldn't, and we wouldn't be able to say much about it. So what came in this wave is a number of formal techniques that could be used at runtime to provide some guarantees. Who is from a formal theory background here? Good. What are the formal models that we can use when we want to analyze a software system? What is an example?
So there are lots, but...
Lots, yeah, that's true. There are lots.
That would be an example.
Sorry?
Automata, for example.
Automata, thanks, yes. State charts, automata, queuing networks, decision processes, market decision processes, right? So, but yeah, so in this particular example that I have here, I'm citing a work that they were using discrete time market decision processes, all right? And here's how they did it. This is a great paper, actually. If you want to really read some inspiring work, this is very, very good paper. So I recommend it. And they wrote something like this. They said, well, we want to translate high-level quality of service requirements into probabilistic temporal logic formulae. Makes perfect sense, essentially, especially if you know what is a TCL, right, or a formula that makes perfect sense, and which are then automatically analyzed to identify and enforce optimal system configurations. Okay? So, also for the rest of you, what actually happened there was that they were looking at some systems like this one here. I will just annotate this one as a managed system, and this is the managing system. You can swap it in your head, and then you have the same conceptual picture. In the managed system, you had some, in that example, some workflow engine and some services that you could change at runtime. And the managing system would have the famous phases. And then in each of these phases, you would do different things. In particular, in the monitoring, what is crucial was, also this one. And you would have a specific adaptation goal in your system. Something like that. The probability that an analysis failure, even if ever occurs during a given period, is less than p equals 0.03. Okay, so that's what we would like to aim for. And how can we enforce this? Well, we can enforce it by basically selecting a different service at runtime. Okay, and this is some kind of model that they used, right? So a discrete time Markov process is essentially a state chart annotated with probabilities, right? Very quickly. It's a kind of, it looks a little bit like that. So you can say, for instance, that after the vital param message state is there, then you basically always go to a state called analyze data. And then there is a probability C that you go into results, and the probability 1 minus C that the analysis fails. Okay, now the whole point that they thought is how we would like to not bind C to a value, right? But bind it later at runtime, and then basically solve the problem of checking the probabilistic formula that corresponds to your adaptation goal at runtime. When we have all the information, or the most up-to-date information of what is actually happening in the system, so we are more ready to give a good value for C. So that was the main idea of their works there, all right? So, and then of course, they many times left also more parameters, right, in their model open, and they will populate these parameters at runtime. I don't know if you have used, for instance, probabilistic model checking before, something called Prism. Anybody? Nice. Good. So now you understand me. So basically, you would invoke, simply put, Prism at runtime. The system would invoke Prism at runtime. If you haven't used Prism, fine. Think about any model checker that you may have used, right? That you basically create a model of your system, a formula, a property that encodes a property that you want to check, and then basically the model checker will tell you, yes, this holds probabilistically in case of Prism, right? Others did not use Prism. They went on the way of doing timed automata, for example, representations, right? And then they used, again, model checkers. That's another nice formalism that helped them say something about the guarantees of an adaptive system. and so on. Yeah, I think this is clear. Essentially, the main thing here is how we represent, right, the information. And that we do with this formal model. Any question? Or any reaction? Something you don't like?
I have a
Yep.
comment. You were mentioning this model checking with Prism.
Yeah.
I think this could correspond to what Joris was presenting before lunch, that they do with this TimeDB hierarchical hypergraph, right? Those queries that they do, that's exactly the same kind of check. That is it holding that I have a component that can solve this, and they, instead of
Yes.
a probabilistic model checking,
Yes.
they were using ontological queries basically for that.
Yes, it's true. Yes, so there are parallels, because what they were doing is that they were keeping, again, they were basically asking their model to do some inference at runtime. What we also do here when we go this way is that we are asking our model to tell us what is our probability of this failing, of this, if I do A and not B, what is my probability of reaching my goals? So that, you see, so that you can take a decision based on the data that you have so far, but of course there's a lot of assumptions that go in there, because you assume that your model here is correct, right? So that you have modeled what will happen in the environment in a correct way, even though you have left some things, and I think the same assumption or similar assumption goes in that work, that you assume that there are a couple, that's what I was asking before, there are a couple of scenarios that can happen. That we all know that, okay, many times there are more than what we can imagine that happens. How do you deal with that? This is something that it's not really answered by those approaches. But yeah.
Here, brainstorming with what you just said.
Yeah.
So to build these probabilistic networks, in the end, we depart from our causal understanding.
Yes, exactly.
So we have a causal model.
Yeah, yeah. It's a very good point, yeah.
So we need to understand the relationship between the variables in the environment, how we affect them, the elements in the system.
I think people that have used, or maybe formal modeling, you might be already aware of some techniques that mine such a model from data. It's very, very important, very interesting, but exactly what you said, it's also my intuition. The causal modeling, because I was at some point fascinated by the idea of saying, well, my whole adaptive system will become an experimentation engine. So I will do A, B, and then I will do a t-test, and I will say, okay, A is better than B. And then I was kind of putting a lot of work and students into this, right? And then at some point I realized, oh, actually, this is just a small version of this whole story, right? Yes, please.
So with Tobias and me, we have been looking at work where they have been integrating ontologies to represent domain knowledge with Prism, and that could be very interesting to look at in this context if you would have suggestions for something concrete, right?
Very nice,
concrete use case. I think that could be a very interesting way of combining sort of domain knowledge with this kind of model checking on the fly. So that would be very interesting from my perspective.
Indeed, thank you. Yeah.
So my question is how practical this could be in applications, let's say in safety critical domain, which you need, the system has to make a decision within milliseconds, for example.
Yes.
So then running a model checker would take perhaps more than a few milliseconds to be able to.
Yeah, it's a very good point. It has. Yeah, runtime model checking, probabilistic model checking reaches its limits very quickly when we're dealing with big models. So people, what they try to do is that they try to work with smaller models or kind of increase a little bit the margin of decision making they have at runtime, but that's sometimes not possible. So there are some crazy ideas. For instance, use the results from model checkers and create a neural network that will create an abstraction on top. This is something that we have played around with, but it's a difficult problem. I mean, of course, you can also try to enhance Prism as well, itself. So blame the solver, right? Not the problem. You can always try to do that. But Indeed, you're absolutely right, and you just nailed the one big problem that these approaches have. Other than that, they are very nice, because they also are nice. They look nice on paper, and they work in practice until they reach the scalability problem. You're absolutely right.
Can I make a provocative comment
Of
here?
course, thanks.
So I see here a lot of science. Like you
Yeah.
take the system and try to understand it scientifically.
Yes.
And we are missing a point here. So these systems, we are building them. We are not studying nature. We are building those systems.
Yes.
That means that we actually have control over the problem. So if
Excellent
that
point.
graph is that big for your system, why don't you go back to Ivano and architect it properly so that you can separate the subsystems? And you can
Excellent. Yep.
reduce the graph that you need to analyze probabilistically to the subsystem, as long as you make the correct assumptions on the external inputs and outputs. And that's why architecting your system, taking the system's perspective, can help us break down this problem into tractable problems.
Yes.
In a way. And coming back to Einar's comment, we have such ontology-based system in which we are willing to introduce probabilities as soon as we have people working with us that understand how to do it.
Yes,
I
not
have
much time.
a 15 minutes presentation on that afterwards.
Okay,
Ilias.
yeah. So I have 15 minutes more, right? So to know what...
10.
10, good.
That's exactly 1 hour, which is what I promised.
Okay, thanks. Yeah, indeed. Actually, yes, to recap this, you are allowed to change your sensors and effectors typically in the systems that you build, which is a very good point, right? So you can add more or less effectors and sensors, right? All right. So control-based adaptation, I can go fast on this because that is something that you know more, for sure, than me, many of you. So basically, the idea was to apply principles for control theory. We'll just try to give you a mapping of the concepts. These are some things that they said in one of the, let's say, seminal papers around 2014. That is our main conference, this International Conference of Software Engineering. This is the main conference in the software engineering domain. So they came and they said, we know how to do loops with a control theoretical formal guarantees. And actually, if you read that paper, there's probably nothing new for you in control theory. Nothing new. But it was quite interesting to the software engineering. That was why it was accepted, and I still remember I was there when they presented it. So they kind of said, look, it's simple. You just have to take a PID controller, more or less, and then you play with the alpha, right? It was more or less the paper. But in the end, it started kind of looking interesting because other people, even themselves, who are very good researchers, they said, okay, well, you have multiple outputs, multiple inputs, different types of controllers, etc., right? The main idea, if you have control theory and you want to model everything as a control theory kind of viewpoint, you will have to start translating things if you want to talk to us. So you have to say, yep, your set point is typically your adaptation goal. Your controlling part is basically your controller or the managing system. Typically, the disturbances, we call them uncertainties. The target system, we call it managed system. And basically, the system model is something that you will build using one of the techniques that Kalman filtering or others that you know from textbooks, right? So this is also important to note that if you have a change that basically invalidates this model, then you have to retrain, right? And if you do that, at least at the model level, you will have some guarantees by design, as you know very well, right? Converges, doesn't converge, we have some range of overshooting that, and then you can give it to stakeholders and they can say, oh yeah, we like this design, actually, that's a good adaptive system because of these guarantees. So they said, instead of kind of trying to see probabilistic guarantees, let's try to put them by design. And of course, many problems can be cast to control theoretical models, but not all systems. Okay, now learning. That's one of my favorite. I do research on that together with Elvin here, who started his PhD. So basically, the idea is how to use learning techniques to support the effectiveness of decision making at runtime. The idea is not new in a way. It was introduced probably by this paper, 2009, where they wrote something like about online learning, online planning in particular. They said in online planning, and a software system can autonomously derive mappings between environmental changes and software configurations by learning its dynamic environment and using its prior experience. And this looked a little bit like this. Are you familiar with reinforcement learning? The concepts? Good. So basically, this is the main reinforcement learning picture. You have an agent, an environment. The agent performs actions and looks at the reward that it gets back and the state changes that may happen. All right? Very, very quickly. So how does this map? So the agent, if you want to really follow this idea, will be your self-adaptive system. Your action will be an action that you do at runtime. The reward will be typically a system utility, some kind of quantification of the satisfaction of your adaptation goal. Typically, you use some weights there, unless you want to do some Pareto optimality, which will be weird. And then the state will be the system and or the environment. This is interesting, Alvin, right? So, and or the environment state. So what is also crucial to understand is that this model does not typically work for adaptive systems. Why? Because you have something that typically triggers adaptation in the systems that we build. You want to say, you don't always have to have a kind of an online optimizer that does reinforcement learning. Typically, you want to trigger this to happen when you are in a situation that you don't know what to do, right? So this is a more complete model, for instance, that basically we have some situation that might trigger you to a new round of reinforcement learning. So this is yet another way to create controllers and create self-adaptive systems. Okay, now this will be a recap because I have talked about more or less everything. So questions. This is a conceptual model. What shall I do if I have a greenfield design? Then you have to look into the tactics of Ivano and start thinking, oh, can I use tactics at runtime? And basically construct my system in such a way that it is possible to use such tactics. If I'm using a legacy system, okay, it might be more difficult to change things, but still, it plays a role. Distributed or centralized system, of course, these are implementation options, and that will change a lot in the end, implementation of your system. But in any case, I think you should start from thinking, what are my adaptation goals? What do I want to achieve by having these extra layers? What can I do realistically in my system at runtime? There are some things that I might be able to do. Typically here, I can play a role. There's a big, things that I can consider. And what are the situations? When should I trigger adaptation, typically? These are things to kind of start thinking when trying to develop an adaptive system. And then I think you have to choose a paradigm, your main paradigm. What would be your main paradigm? Would you follow some architectural model, which I won't talk about because it was a whole day, more or less, about architectural models. Would you use control theory embedded in an architectural model? Of course, the paradigms can also be, but one has to be the primary. Would you use the reinforcement learning? Would you use something that is very close to reinforcement learning, which we might call online search or online optimization? Something else, right, that I probably missed? So this is a decision you have to make. I will skip this one. I wanted to explain how we can cast the problem to online search. Basically, I have done this work where we use evolutionary algorithms to do decision making at runtime. Because all the other, I think I talked about, apart from this one. Then finally, there are smaller decisions apart from the main paradigm that you might want to think about when developing, for example, your analysis. So you can do simple threshold checks, right? You can do something more complicated, like ordering of adaptation options by expected utility. You can just try to kind of shorten the number of options you have, etc. Right? These are analysis, what you can do in analysis. In planning, the same. Actually, you can implement a self-adaptive system using something like rules. I don't know if you have used this in Java. No? Okay, this was too software-y. But anyway, it is basically event condition actions, right? So you can implement your own language, use languages that exist. You can use well-known formalisms. You can use even within the planning phase such a paradigm, right? To try to at runtime do online planning. Okay, I'm almost done. Just a glimpse of what do the practitioners say, right? So we tried last year to ask practitioners in a bigger survey, online survey, a questionnaire, what do you think are the problems, right? We're doing this research for 20 years, right? Is it something relevant for you in the end, or were we really off track? okay, we asked different people from our contacts. We're a bigger team, so we had different contacts and different roles. And this is some of the answers. So they said, for instance, give us a use case, we told them. And they said, well, what is the subject of adaptation? We, of course, did proper labeling and everything. So, and many people said, okay, the whole system is what we adapt, or a module of a system. And what type of adaptation do you do? Autoscaling is still predominant, right? It's something that has been it's actually used in practice. But also auto-tuning, that was a funny one. Somebody said, yeah, we have this feeding robot, a Ming feeding robot, and we auto-tune, and we believe this is self-adaptive because we auto-tune the amount of food that we give, right? That the robot gives. So, and then again, what was the trigger of adaptation? And they mentioned, okay, loads, different events, environment properties and system properties. That kind of was nice for us because we said, okay, our categorization of uncertainty is probably good. It can encompass different aspects. So, okay, this is ongoing. Good. Almost done. Open challenges. One thing I believe is very important is how to deal with unknown unknowns, right? If you have a system that you can think about everything that could happen, you can engineer it. What about things that you cannot think about? What should the system do then? Not very far from the systems we want to build. Actually, self-driving cars will probably fail because of this problem. Explainability of runtime decision making. That's a huge one because people won't use these systems. If the robot starts doing different things, and you know, you need to understand what it's doing. And actually, it was a good example that the robot would tell you what it was doing. I found it very nice. So it was a very good idea. Another super important challenge, very software engineering, is, yeah, we need methods that support the whole life cycle here. We have some things here and there that make sense, but we want to put things together still. And of course, we need the realistic test beds because we are at a level in this domain that we want to we want to mature. And at this point, the realistic test beds, and perhaps also you working in robotics, right, is super important because otherwise it will always be some kind of small experiments that we do in our labs. Yeah, so I hoped I was trying to convince you that uncertainty is the main driver behind these systems that we call self-adaptive. They have great potential, and basically the grand challenge is still there. I mean, we have done a lot, but there is a lot more to be done in how to tame uncertainty at runtime. That's it. I want to close with reminding you that some of you know about it, but we have actually a community website called self-adaptive.org. And there, among other things, you will find exemplars that you can try to use. Many of those actually are related to robotics. Some of them use ROS, some of them don't. Exemplars are systems that we use in our evaluations to compare different methods that we build. Okay? And yes, a lot of the things that I talked about are nicely summarized in this book. I have it there, so you can give it a quick read now. And also, if you don't want the whole book, then you can just try to find this one. It summarizes a little bit these waves. And of course, these are kind of legendary books that came out of Daxter seminars in this community that are also good sources. And you can check proceedings of SIMS and proceedings of Axos. I'm co-chairing Axos this year. So, yeah, and here are a list of references. Thank you.